Hi, Jay.
resource person Jay Ganesh
Hi,
sir. Hi Jay
hi,
Ganesh
ma'am.
sir.
Hi, ma'am. Hi,
Welcome to
ma'am.
second day, second session for 6-day
Sir,
FDP.
you turn on your camera, sir.
Okay,
We couldn't
I'm
see you.
sorry.
Hmm.
Just a minute. Actually,
You
I
can
have some
share
issues with
you
my
share
camera,
your
ma'am. That's the
screen,
problem.
but you please turn on your
Okay.
camera, sir.
Yeah, that's what, ma'am. I have some issues with the camera, ma'am.
Okay, no
Sorry for it.
problem,
Yeah,
Jay.
Oh,
yeah.
isn't
Yeah,
it?
it's fine.
Okay, okay.
Yes, yes,
Yeah,
yes.
it's my
Okay.
pleasure
Then
and
you can
gratitude.
share your screen, first page of your PPT,
Sure, sure. Of course,
so
ma'am.
that
Of
we
course, I'll
There
can,
do
it
it now.
is.
madam can start the session.
Yeah, ma'am.
Introduction.
Yeah, so it's our pleasure and gratitude to introduce our next speaker, Mr. Jay Ganesh. Jay Ganesh is a senior AI architect. He is an architect lead at Valeo India with over a decade of expertise in artificial intelligence, machine learning, deep learning, and robotics. A renowned trainer and an international speaker, he has conducted 800 plus workshops and guest lectures across IITs, NITs, IISc, and leading global institutions. He was recognized as a Speaker of India Book of Records for leading the largest AI workshop. Jay Ganesh has also been a Smart India Hackathon judge and appreciated by Dr. Honorable Dr. APJ Abdul Kalam sir for his contributions to robotics. With 11 plus years of professional experience and impactful research contributions, he continues to inspire and shape the future of AI through innovation, training, and thought leadership. Thank you so much, Jay. We are proud enough to introduce you, and we thank you for accepting our invitation and being with us today in delivering a session titled Gen AI for Image Generation. Over to you, Pam.
Yes, ma'am. Okay. Yeah. Thank you, ma'am. Thank you so much for your great introduction. Yeah. Thank you. Everyone. Very good evening to everyone. So, whoever present here, my warm greeting to all of the one of them who is presenting here. And today, I'll be start talking about the topic of GAN architecture. So one of base generative AI architecture. So of course we know it, right? So we are in the era of generative AI era, and we start like we have a AI and machine learning and deep learning, and after that now we are in the era of generative AI architecture, and we have enhanced to the agentic AI now. So now, if you ask me like where GAN architecture it fits around, where this particular GAN architecture it fits around in the sense in the deep learning architectures. In deep learning architectures, we might have heard about like a CNN architectures, and further that we'll be having like a GAN architecture. So CNN architectures and based on a lot of pre-trained models, we have everything. But this particular GAN architecture is a very powerful, complex architecture in order to generate an images. And this is a origin. This is a very base origin for all the generative models what we are working in the current industries. So for example, image basis in the sense now we have, so for example text basis in the sense we have a transformers and encoder decoder models and OpenAI, Gemini, and everything we have based on the text model. So when you coming to the other side, so other side of the coin is like a images. So if you go for an images, we have other transformers is like a vision transformers and everything. And how this vision transformers and everything starts from in the sense from the architectures called the GAN architecture. So let me take it through the presentations and how the architectures looks like and what is the benefit of this architecture and what are all the research areas are available in this GAN architecture. What are the research areas are available in this architecture, what are the gray areas we can able to look around in order to put our efforts to make some researches, everything I'll give you an insights on it. Okay, let me begin with this. So already you all have got enough introduction about me, so you all know about a deep learning. So yes, of course. So when we started to talk about GAN architecture, we also should have insights of the previous architecture. So for example, consider we have a complex neural network architecture. I have images, and I'm giving that image to my machine. So I mean my architecture. My architecture can able to classify whether what image it is, whether it is a dog or any other animal or something else. It can able to detect it. That's what object detection can able to do it. And where we have in the sense that we have another architectures where we can give data like text related, and it can able to translate and everything like in French translation, Spanish, or whatever it could be, it can able to translate. On the other hand, audio classification of course is relevant to the language translation. And whatever you look around here, whatever you see out around, everything is like a discriminated models. Am I right? So if you give some data, it can able to understand what it is based on what presents in an image, and it is not able to give you a new content or something else. If you give an image, you are asking whether it's a dog or not, it will say yeah, it's a dog. Based on my knowledge, based on my understanding, I agree that this is a dog. And if you give some kind of text in the sense like I love pancakes, of course you we have trained our model by using our complex data sets. We can able to make our model to understand what is the exact word resemblance for that I love pancakes in French. So similar wise for an audio. So now we can able to understand we have worked so far in the discriminations models. Okay, discrimination model, but now we are into the era of generative model. So what is a generative model? So if I ask a same question, I love pancakes, I am expecting my model to tell about how the pancake looks like and how to prepare the pancakes and where the pancakes are most favorable and how we can able to make a business through the pancakes and everything. It needs to give you a next level of insight. That's what we are expecting through the generative models. And if you step back, okay sir, you said that the GAN architecture is a base architecture, and so why did you mention like a variational auto encoder right here? Yes, that's a one insight I need to give it to you. So anyway, so father of father of generative AI for image specific like a GAN architecture, and father of GAN architecture is of course is like a variational auto encoder. So variational auto encoders generally it's like an encoder and a decoder architecture. And if a given image, it extracts the features from into it and it stores in the latent vector spaces, and through the feature we can able to give it to decoder. That decoder can able to decompose this data to compose it as a as image as an image. Likewise it will give you. And you can ask me a question, okay Jay, there is no new things we found right here, right? You are giving an image and it extracting it, and we are storing in a latent features in a vector space, and again we are retrieving it back. What is the use in this? Like you can ask me. That's how auto encoders works for. So auto encoders is more or like for image compression techniques, and very fewer places of image decoding era so we have used for that is a way we have used for the auto encoder. And next level is like a consider. Now consider, do you have an image and given to the architectures and we can able to give it. Now this particular cat data, right, you can consider in terms of embeddings, like image embeddings you can consider, and you will be having some error. So in that place you have stored all of this data, okay, all of this data, and suddenly you are picking some gray area and you are asking a question to a model. So maybe I can um, take this paint actually. So now you can see about it. This is your latent space. I hope my screen is visible. This paint place, right? Please can someone acknowledge because I'm. Is my screen visible to all? This paint what I'm
Yes,
showing
yes.
right here? Yes, ma'am. Perfect. So now
Yes.
consider like yes, ma'am. Thank you, ma'am. So now you are giving like a dog images. So the dog images right here it is storing. So this is a place where you are storing a dog images, and you have a what is that cat images. That embedding. So we are storing in a complex vector space, and this we represent as a dog. This cluster and this cluster will represent as a cat. Now the make thing in the sense like now the user asking some question about a horse or some questions about a small tiger. So my question, my embedding will fall around this place. If I retrieve this area, of course I'll be getting a noise image as like this. Am I right? Okay, so you will be getting like a the noise image like this. And also if I ask if my question falls in this cluster, then I can able to expect my model to generate a dog image as it is. So you can ask me, Jay, we have extracting an images and we are taking those embeddings and we are storing those features in a vector space. Of course, if you ask a question about that cluster, then only we can able to retrieve it. That's of course true. But then how we can able to convert these auto encoders to what is that image generation model? So that is the next research level is happened the samples from the distribution. So what is the samples from distribution concepts they brought in the sense in the neural network era? So you have a various data, that's not a problem. Okay, you have a dog images and you have a cat images and you have storing another set of images, like here you can consider like it is a horse images and whatever data sets. Of course, right, when once you step into like a GAN architecture or we are going for the complex architecture, you have to train your model with the ample amount of data and ample amount of different amount of data. Then only your model can able to potential enough to understand the scenario. So now horse images and here tiger images and everything. Okay, now I have this environment is present. Again, here also I have a same disadvantage. If your question it falls cluster, then I can able to retrieve that part and I can able to generate images. Again, if it falls in the any gray area, it will not able to generate. So now what they have brought in the sense, they have brought the concept called continuous region. Continuous region in the sense connecting all the region values one with other. So what are all the values? So from I have some value here, I have some values here. These are all the mystery area. So what I can do in the sense, I'm doing some interpolation. Using some interpolation concepts, we are connecting these areas. So like this, we are creating a continuous region. Okay. So cause of this continuous region, now you imagine. Now I'm asking a question. I need an animal. I wanted to generate an animal with the dog face, with the horse tail, and the tiger body, and with the cat mustache. If I'm asking question, that question may fall somewhere around here, consider. So now my model have all the features ready on his vector space. Now it refers all the datas and it can able to accommodate them everything right there, and it can able to generate you the respective image what you expect. Okay, this is how actually the variational autoencoders is started to enhance their model to develop and to generate an images. This is what I said it. Like you can able to see they have a dog distribution, giraffe and cat distributions, and we are connecting them in a single continuous region. So if my questions are everything connected in a continuous regions through transpolated, what is it, okay, what interpolated, now I can able to make my model to understand what questions users ask, based on that extract the features and generate an images. Okay, of course, if you ask me like, oh, okay, then variational auto encoder is a best model ever when compared to GAN architecture. Of course, it's not. So there was some drawbacks out there. I'll tell you that. So how your actual models looks like, your encoder architecture, your decoder architecture. So earlier before variational auto encoder, we will not be taking like different distributions. Like our latent space distribution will be like a common mean, or it could be a variance. So now whenever you are extracting an images, extracting the features, it stores the features as like a mean and as well as a variance. What does the mean and variance actually make sense here? So now consider I have one dog images. Okay, I have one dog images, I will be storing in a some vector values. Okay, so I have a vector value about how this dogs looks like when compared to other dog image. That is my mean value. And also I have a variance vector. So that variance vector tell me how this dog image differs from other dog images, and how this dog image differs from a horse, and how this dog image differs from a tiger. Likewise, the complex vector it will be there. So consider now my architecture, it's extracting the feature in terms of means and in terms of variance for each and every images, so that it is understanding how the each and every features looks like. So now if my question falls anywhere under this vector space, it has a mean and it has a variance, it fit it around in some other era, so it can able to understand, it can able to generate an images the way we expect. Okay, so this is what actually how the variational autoencoders and what is that the GAN architecture also, of course, it's using in the backend the similar concept, but they have enhanced concepts they are using. Okay, so now if you ask me about what is the prime differences between these two, like auto, so variational autoencoders and GAN architecture, on the right you can see. So GAN architecture, a very complex architecture. It is constructed with a generator and a discriminator. It does plays like a min-max game between them. And when you go for like a variational autoencoders, there will be a reconstruction loss you can expect and a latent loss you can expect, of course. And consist of a generator and a discriminator networks here, and consist of encoder and a decoder. This architecture is more or like used to generate an images, but it is not that much powerful by using a deep neural network concepts on top of it. And how stable training it is, it's like a Nash requires of a Nash equilibrium during the training. And when you go for a variational autoencoder, it's like a end of training phases. It's completely a closed solution, and it is focusing on end of training phases. But your GAN architecture, it raises a question between your model itself while doing the back propagation in order to fine tune the generated images between a generator and a discriminator. Okay, so now you'll find the difference when I'm specifically talking about GAN architecture. You'll find the differences, and if you see the outputs of an images, variational encoders do generate a face images, dog images, any images, any data sets you wanted to look for, everything of course it will do. But a GAN architecture generate an images with the more sharp and with the more clarity, with the more pixel quality values you can able to expect, but variational outcome do fail in noises and everything. So this is a prime differences between autoencoders and the GAN architecture. Now I'm stepping back to GAN architecture. If you focus on GAN architecture, Okay, if you focus on the GAN architecture, we have to stick around these images because this is one of a fancy images. So because I was taking this session like a 2019 from, but at the time and all, GAN architecture was mesmerizing one. People do amaze by seeing this slide and all, but of course nowadays people do not amaze. I know it, right? Because we are seeing an a portrait, so we are seeing a generated images using VO3 and Gemini, so VO3, and as well as what is the next gen videos kind of things are all generating videos itself. And we also get practiced through some movies now, one of them Tamil movies, Telugu movies, and also in some Hollywood movies we have been get practiced to by seeing the different images. And of course this is a legitimate of course for me. Okay, so we can able to make the beautiful Mona Lisa to talk, and we can able to make our the great scientist Einstein to talk. Okay, so now again architecture is not of course a new ideology. AI is not new ideology to us, but of course that GAN ideology is also new to us. GAN architecture was introduced at the time of 2009 itself, 2008 9 itself. There was some research papers came in the market, but the reason is not possible is nothing but we don't have a hardware configuration, hardware capabilities. So in order to run a one architecture itself, it's a very quite hard in any of the platforms, any of the CUDA engines or something else. But now we have evolved like after 2008 in 2019 that the Nvidia has rised like anything in their developments. We started to work on the parallel mechanisms, and we have a quantum computing and everything. We came into the market. So of course these kind of architectures became true. So it makes researchers became true with their ideologies and everything. So now, so what is the role actually this GAN architecture will do? So we have a two architecture, as I spelled out before. We have a two architectures. One architecture is purely a generator. It can able to generate a new content based on the references you given to the model. And a discriminative model, what it will do in the sense, it can able to discriminate it whether the generated image is a correct or not, whether it is a image or B image. Likewise, it can able to discriminate what your image is all about. This is how your discriminator part will work. Now, so now you can see these images. Now you can able to see slide. What does generative model generally do? Okay, so now generate a model, a distribution which closest to the closer distribution. Now you can see this example, the similar example I'm going to show you through an hands-on. So I'll take you to this hands-on code after the session. And in this hands-on session I will be going to give a set of data sets to my machine. So I'm going to give some sample data to my machine. I'm going to generate 100 samples, I'm going to generate 1,000 samples, I'm going to generate 2,000 samples for my project. So now you can able to understand what is the exact usage of this GAN architecture with respect to research and with respect to academics. Yes, it makes a huge impact. It makes a huge impact in kind of development cases and the data set preparations. So of course we know it, right, how hard it is in order to prepare a data set, in order to look for a data set to generate and all, right? So now how Kaggle and Hugging Face and how other ImageNet kind of thing, how they are generating an images by using this kind of complex architecture. If you have a good samples of 100 or 2200, that is maximum enough in order to generate a rest of the images the way you want. So the images, coming to these images, now you can see on left, this is completely a noise image. Doesn't have any knowledge at all. This is completely a noise image. Now this is my model distribution I represent right here. And when you go for right at this place, this is a target distribution. This target distribution, this is my final output. This is what I'm telling to my model. I'm expecting you to generate a similar kind of images by having the base model distribution as a noise images. This is what I'm giving a sample to my machine. Now my model started to understand. Both my architecture started to play them around. So now you see earlier attempt, now you can see earlier attempt, my model started to understand. My model distribution is trying to reach a target distribution, and the overall the time period, they started to almost attained the target distribution the way we expect. Okay, this is the same example. I have it in the hands-on so that you will be having a better ideology. So this is what actually I spoke about in the, what is that, in variational auto encoder and the basic framework. And this is how your basic architecture, the basic framework of your GAN architecture looks like. Now you see this is my generator. Okay, now I'm giving a latent space. This is my latent space. This is some noise image. This Z represents, it's a very noise complex images. Now this noise images I'm pushing into my GAN architecture. So my generator is a potential enough to generate a very different fake samples. And according to generator, it believes that that is a true images because your generator doesn't have any knowledge at all. We have a back propagations, we have a cost function comparisons, we do have a optimization within them. Of course they do believe that the image generated images is like a true images, but when you are giving these generated images to the discriminator, there's the place status around. So in this discriminator, it takes your fake samples, and of course in order to compare, whether it is a original image or a fake image, to identify, your discriminator requires a real samples. That means the ground truth data. We provide our ground truth to right at this place. Okay, now we are giving this both inputs, we giving this both data to the discriminator as an input. Now your discriminator started to compare with these features with that features to ensure whether it is a valid data or not valid data. So this is how actually your architectures is communicating between them, how discriminator identifying the generated fact samples is a true samples or the fake samples. This is how your generator trying to try to cheat your discriminator. Okay, so more on a framework wise, I will be speaking around with some equation part. This is what I have prepared my source code also. Now you see that this is my real sample. Okay, this is my real sample. Now I'm giving this real sample to my description, I mean sorry, discriminator. Now my discriminator taking this discriminator d of x, that means probability distribution of x. Okay, the probability distribution of it's a vector value. Okay, this is how d of x is represents. Now when you speak about like a generator, z values, that means they're random samples, it's a noise data, we are giving it to the generator. Now your generator takes the data and it generates an images. That images we represent in the name of, in the proportional of like a g of z. Okay, in the angle of like a g of z, generated fake samples. That fake samples we are issuing it to the discriminator, and now the discriminator is generating a final samples is like a d of g of z. That means discriminator, it's taking the sample of g of z. Now it is calculating the probability distribution of g of z. This is a logic, we will be having a complex vector structure. Okay, this is how actually I've structured a code. Also I created an object for my generator as a g and a discriminator as a d. That's how I have represented in the same way here. Now you can ask me, okay Jay, now you said about all this, now I wanted to understand how the loss calculation is works right there. So of course the GAN architecture is also a normal CNN architecture, how we dealt with the same loss calculations we work around. Now you can see discriminator loss. So discriminator loss is depends on what, it depends on your ground truth data, and it depends on your fake samples which generated by the generator. Am I right? So that's what I had mentioned here. So how this logics are expecting, so d of x, that means discriminator takes a real samples that near to be one. That means always it's supposed to be one. Okay, it's always supposed to be one. So d tries to make d of g of z near zero. So that means sorry, so d of g of z near zero. That means your discriminator's prime role is always to determine the generated samples or the fake samples. That means it's a near zero. This is a log, it's actual the maximum proportionality we will be having. So through this value we will be calculating the generated samples or equal or not equal. Likewise will become loss calculation, right? So this is a ground truth value for your to compare with the actual images. So now this is a final equation, d loss, which is equal to, for real data for the discriminator, dxl ones, and the loss data is the ds zeros. Okay, so now you can ask me, okay, how about the generator, Jay? Will it generate with, are we treating a generator as a normal CNN architecture? Are we calculating the same loss calculations for the generator also? Of course we do that. So for generator, its primary motto is all that d is g always tries to make d of g of z is one. That means generator always focuses to cheat the discriminator as a one. So that is the how the equation is represents. The cost functions we know it, right? We'll be having like a um, many functionalities like so Manhattan cosine distance and the cosine similarity, Manhattan distance. Likewise we will be having like a cosine, I mean what is that, the cost functions in order to calculate some things. Now, so training discriminator, so how the generic processes happen between them is all about nothing but the back propagation. So generally the back propagation do happen within the discriminator, and also the back propagation will happen within the generator, and also that back propagation will happen between discriminator to generator. And that means like it is not a overall or each and every epochs it will not communicate, but you can consider that to the final updated weights will be transferred to the generator. Likewise we can consider, think about it, now you can consider running a single architecture how complex it is in our configuration or something else. But here we are running two architecture at a single moment, generator and the discriminator, both of them are running simultaneously together, and they are share they are 50 epochs generator, 50 epochs discriminator, and between them there's a 50 epochs. Consider, I mean it's not exactly a thing, this is an illusion idea I'm giving to you. So think about it how complex your architecture is all about now. Okay, but most of the people thinks that okay, discriminator it not sharing a data to the generator, I mean not sharing this back propagated final weights to the generator. Consider that your generator doesn't have any real samples or something within that, it is having only the fake data, I mean sorry, noise data. That noise data will be shaped up some other way. Your discriminator is supposed to navigate your generator to give some ideology to generate a actual images what it expects. Okay, so now other part is like so okay, now I'm working on a GAN architecture, so I focus on the generator because that's a prime role which is focusing on. So discriminator I'm making it a too lenient. If you do that your model will fail. And you would have think about okay, discriminator plays a vital role when I'm seeing from the top end, so it's going to compare that, it's going to compare with the generator, so I'll make generator as a linear model and discriminator as a powerful model. Of course your model will fail. That means you have to construct a generator and discriminator, both of them are equal weight. So having said that, equal weight in the sense, generator if you are using 100 layers, and the same 100 layers you need to construct with a discriminator, I didn't say in such a way. So generator is of course a powerful model. If you construct with the 100 architect 100 neural net 100 hidden layers in the sense, your discriminator of course supposed to be like a 30 hidden layers or the 40 hidden layers, because however it's going to be like a comparing the models. Okay, so now because if I sell it to the people like you have to construct both of them is a very complex, they build a generator and discriminator like 100 under hidden layers, and they are adding the optimizer, complex optimizer and everything. So there is ideology, so there is an ideology will be there. Yes ma'am, please. I raised some hand, sorry, I see some raised hands. Any questions? I see some raised hands. All right, okay. So now I'm stepping back to the GAN types. So different types of GAN, as I told before, like the GAN zoo. So now, of course, it's a zoo. When this GAN architecture came into the market at the time of 2015, 16, and all, there was no papers at all. There was no research papers. There was no modules. There is no libraries, attractive libraries to construct a GAN architecture and everything. But now we have a lot of sources, a lot of research papers are came into the market in order to approach, in order to elevate the GAN architecture. So that was like initially it was called as a vanilla GAN. Now this vanilla GAN is being migrated to different GAN varieties. So I'll show you some things here. So DC GAN, so deep convolution GAN. That means if your samples is images or complex images, and since you are upsampling, that's your generator and discriminator, both of them should be a complex deep neural network, deep convolution architecture. For example, if you are having like a conditional GAN, now you are going to generate a samples, I mean the training samples for your particular problem statement, and you will be focusing on. So consider like a hard disk for cancer classification. You have 100 samples or 1,000 samples, and we are expecting like other 1,000 samples or 2,000 samples to be generated. You are constructing a GAN architecture, and you are giving like a, you are giving a condition. So when you are generating some cancer images, create a resolutions as like this, and these are all the areas I'm expecting the clouds to be available, and these are all the areas I'm expecting some noises to present. Likewise you can add the condition right there, so your model can able to generate in such a direction. So that's what, so you have to give the specific conditions, like I'm trying to generate and face images here. So it's a male face, black hair, blonde, makeup, and sunglasses. These are all the attributes I wanted to fit around. Of course, these same attributes you have to add it on top of a discriminator, so that your model compass along with this feature to discriminate and to generate a matrices for it. Okay, so now, so BiGAN, so bidirectional GAN is nothing but both the GAN should run with the embedding data. So that's what actually the bidirectional GAN. So you can ask me, okay, so now are we able to create any new GAN by our end? Is it possible? Of course, it's possible. Think about it like a for any linear problem statement, you wanted to use like a GAN architecture, create a one architecture in the name of linear GAN. Or if you have any non-linear problem statement, you can create a one research paper in the name of like a non-linear GAN. Likewise, you can able to create, or else like a linear composition GAN, non-linear because these are all the ideas I had in my mind, but I don't have a time to create any of those. So maybe you can create a new ideologies, new ideologies and new research ideas through this GAN architecture. Still it is going on. GAN architecture is still there is a under research. Many researches are happening under this GAN architecture. So the vanilla GAN still is in the market, so people have started to add up their flavors on top of it based on their problem statement. The lot of research papers came. Okay, so now you can able to do this kind of GAN varieties on your own. So what is the model definitions? Yeah, of course, if your problem statement is all about like arrays, or if your problem statement is all about pandas data frames, in the sense your generator and a discriminator, both of them should be like a fully connected neural networks. If your data set is more or like images, in the sense, of course we have to go for convolution neural networks. Generator and a discriminator, both of them should be like a CNN. And whereas if your problem statement is all about NLP based problem statement, you must consider a generator and discriminator. Both should be like a RNN architecture with LSTM cells. Okay, this is a flavors we have to choose upon based on the input, so we go for. And training, and as I told before, right, you are making lenient generator and discriminator is powerful. There is no use. Your model will fail, of course. Okay, because it's a competing between a D and G. It's a competing between them, and there is a alternating executions of a training steps, because generator executes from some functionality and the discriminator some executes some functionality, and they both together they both communicate some weights among themselves in order to educate the generator by using like a discriminator. And using like a mini batch stochastic gradient descendant is nothing but because in order to make your model to understand with respect to the fewer samples, and so that we can able to go use for like a mini batches GD descendant out and optimization techniques. And here you can able to see some equation representation, and this is nothing but is a min max version like a G and a D, and vanilla GAN, so DG V of D of G. So it's like a summation next P of data, so that means overall samples, the real samples, and logics of D of X. This is nothing but discriminator of real samples. This is a proportionality equation for real samples to compute accuracy for real samples, and for the generated samples the summation z equal to p of z. That means the overall samples logits of 1 minus d of g of z. Okay, that means like a d of discriminator which takes a generated samples, generated takes us noise samples, so generated equation. So now you can able to understand this one. So what is the d of x we are expecting? That's always supposed to be 1. Am I right? So classifying the real data, it's we are expecting the equation to be 1, that particular value is supposed to be 1. But the classifying the wrong data, that means your generated samples equation is like a d of z of z1. So that means like if your model is classifies the wrong data, it matches as a 1 again here. Okay, so this is how the discriminator needs to understand the real data and as well as the wrong data. So the discriminator is an adaptive loss function. Yes, of course, we'll be focusing on the adaptive loss functions to make your model to adapt with the loss values and the proportionality values, and altogether like almost the same actually. So this is a min max, it's not that much requirement. And this is all about like how the training of your discriminator looks like, almost the same actually, the same equation what we have seen upon there. Like in order to compute the performance of the discriminator, we will be using like this equation, like g of which is equal to 1 by m summation equal to 1 to n the overall real samples logits of d of x. And this is for fake samples, is for overall data. So for the D performance, in order to perform like how good D is, so we'll be using this is a performance, how good my model is going on, what is the precision rate. This is how it will be choosing based on this equation, based on this outcome we will be updating the weights of a discriminator. Okay, so similar wise for the generator, so we'll be having like a D of G of Z, so overall performance based on this we are updating the weights of generator. Okay, so this is a performance which is happening during the time of like a loss calculation. This is how you calculates and determines whether your model has a good weights or it needs to be updated with the fancy weights. And the GAN applications, yes, of course, there was a lot of fancy applications roaming in a market like a face generation and domain translation. So domain translation, when I say about domain translation, something is comes to my mind. Um, so nowadays, right, maybe I can show one video to this so that you can able to understand what is the domain translation I mean. And nowadays we have a lot of products, right, the handbags and the car designs, and also like the lot of bikes, different bike designs like a sports bike designs and all. So nowadays we are not setting us particular persons to structuring that in order to create a new designs. Of course, we are using a GAN architecture in order to generate a new samples by having the existing samples and over on it. Okay, that's how the complete what is that the our entire world has been moved on. Now we have been migrated to the VLMs, and we are working on the GAN architecture, so very complex architecture. Now we have stepped into the transformers. So through the transformers, we are having a visual language models. So, but anyway, whatever you say, still GAN architectures in the market, in the many of the CG techniques in the movies, right? There and all you can able to see still GAN architectures are in the market and they are using for it. And semantic image synthesis is, so we can use it for like GAN architectures, of course. Super resolution, yes, super resolution. We can go for a CNN itself. It's of course you might have think about it, but however, GAN architecture is also takes place of using like a image super resolutions kind of things. This is sorry. So, so some of the research and some of the links and studies what I have done so far, I have added on top of these slides. You can take a look at it once I'm sharing this presentation with you all. And some of the YouTube channels also I have referred. So everything I have had it right here. Okay, this is my contact. So time for an action now. So any doubts with respect to the presentation so that I can take you to the hands-on now? Any doubts or any queries?
Participants, if you have any queries, kindly raise now. Sir is moving to the hands-on session. Sir,
Let him
P.
continue.
Kokila, madam, has
Yes,
raised her
ma'am.
hand.
Yes,
Yeah,
please,
hello,
ma'am.
sir. Yeah, hello,
Uh,
sir. Good evening.
Very good evening, ma'am.
Yeah, your session was very informative
Thank you, ma'am.
and
Thank you, ma'am.
very interesting too, sir. Even though the so many concepts were already known, the mathematical part which you have explained, at the beginning, it was very impressive.
Thanks a lot, ma'am.
And uh, I have one small question. See,
Yes.
nowadays the concepts of converting 2D into 3D is increasing.
Mm,
Okay.
mm, mm,
So there are a lot of complexity. If you're taking a satellite image, we do face some sort of complexity like analyzing the depth, all those things.
mhm,
And converting a 2D medical image to 3D, we do face some other problems like granularity, all those things we have to take care of to identify the exact pattern.
mhm. Yes, ma'am.
So to bring on much accuracy over 3D scene creation under any
Mhm,
domain, maybe it
mhm.
can be healthcare or in satellite image or whatever may be.
Okay, ma'am.
So, what kind of tool or the technique you will suggest us?
So tools in the sense, ma'am. So in order to convert like a 2D to
A
3D,
3D
right?
image, or like with the techniques where we can develop everything from the scratch. Uh, from the scratch, if there are some techniques like you have mentioned, no, the vector map which you have shown in your
Mhm.
inputs, I mean through the slide, I could
Yes, ma'am.
able to find that
Mhm, mhm.
there is some scene generation through vector map you have generated it, right? So
Yes,
which
ma'am.
kind of technique would be more suitable for 3D scene generation under for
So
any domains?
for any domain, so your major thought is like will be having a 2D samples in your hands, and you wanted to convert that embeddings into the three dimensionality, and you wanted to regenerate that images through the 3D wise. Am I right?
Yes, yes,
So yes,
yes.
ma'am. So actually, for this case, you can able to use like a GAN architecture itself. But thing in the sense of what is a one complex area, what we have to focus. You have to use a encoders first, ma'am. You have to extract the images. Technically, I'm talking about through the architectures wise. You have to extract the image samples and as a features, and you have to store it in some vector embeddings. I mean, sorry, not vector embeddings, like a feature extractions, values, everything. Now what we need to do in order to convert that images, that values into three dimensionality, you have to add other samples, like you have to add other samples, or you have to convert those values into some numbers by using some of the additional architectures in the GAN itself is there in order to convert your images to 3D. So you have to take the extractor the features, give it to the architecture, and add additional numbers on top of it to the 3D samples. Then you have to give it to the discriminator. In such a
Mm.
way we can able to do it, but the reconstruction loss will be very heavy, but we can able to fine tune it, but it's a quite really hard. So some of the now if you ask me, okay sir, what is a real easy approach in order to do this? Of course there was a lot of VLMs came into the market, visual language models came into the market. So those VLMs which really helps us in order to convert your images into the 3D images, but what's the problem in the sense, it costs more. So we have to invest some pennies on top of it in order to acquire the tools to convert most of your samples to 3D.
Mm.
So
Okay.
architecture wise, if you ask me, it's truly hard, but a GAN architecture will help. Will it help? Of course it will help. As I told that you have to extract the features, and there was some specific tools are there in what is that, in Google itself you can able to find some of the tools in order to convert your 2D values to 3D, and then you can give it to the discriminator. Your discriminator converts like inversion data to the enhanced models.
Yeah,
That is
latestly
the
we had come across one of the tool like Dino V3.
Dino V3.
So
Yes. Yeah.
Dino V3
Yes, ma'am.
latestly,
Correct.
like 2 weeks back, we have seen that. It is
Yes.
also quite good, impressive. So, but still,
Mm-hmm.
we are not satisfied. We did not achieve better results. So I thought that you would be, I mean, you may have a better suggestions to tell.
That's what, ma'am. Again, I'm saying like
Yeah, for sure.
you can go for like a style can and everything,
Yeah,
and
yeah,
specifically like EG3D utilizes like a triplane presentations to create a high definition 3D composite images with fewer parameters. So you have to use in such a way of tools, ma'am. So
oh,
EG3D, so these are not triplane representations. So you have to take it that, and it also demonstrates that the optimization based on the method works well with the style can too. So based on
mm,
the backbone of like a EG3D. So that
yes.
means it's enabling the real world images to be converted to 3D.
Yeah,
So
yeah, yeah.
that is what actually this is a tool. And so the EG3D is also is nothing but it is also a tool actually, but that is a backbone for your style GAN. Style GAN is a nothing but like it takes your images and it will be changing the dimensionality of your images and everything. So as a backbone, you have to use other triplan representation as a EG3D. So that what helps in the sense I told you, right? You'll be taking the
Yeah.
data and it will be
Mm,
adding some other values on top of it to convert that images into 3D, and you have to give it back to the style GAN to discriminator that will be generating an images in the 3D. Actually I have some source codes, but I
uh,
am not sure exactly. I do, maybe I can check it in my repository now. Maybe I can just give it to you in this session, ma'am. That is like
yeah.
nothing but actually Mintra app, right? Exactly. Simple example is like a Mintra app. So Mintra app, when they have came into the market, at the time they have used the same GAN architecture. So
Mm,
to attract the user friendly. So if they pick some pictures, sorry, if they pick some what is that, dresses or something else, that attire how it suits for the particular women or men. So that is how actually they have created. That time they have used a style GAN architecture with the backbone of EG3D mechanisms. And of course, ma'am, you can expect very bad results over the time period. You have to run it for the lot of epochs we have to run. So with the fewer epochs, we can't expect the quality amount of 3D or something else. We require some powerful engines on our hand. You have to run in your model for almost some greater epochs. Then we can experience some amount of realistic outputs, ma'am.
yes, sure. Surely we will
Mm,
try on. Thank you
yeah,
so
ma'am.
much.
There was some papers also, ma'am. Maybe if you can try it out, like from 3D, from 2D portraits to 3D realistic. There was a GAN inversion paper will be there, ma'am. So
Oh,
author
okay.
is I think Young Joe. I think so. Actually, Young Joe is an author, and
Mm,
it is a paper from like a Michigan. Actually, maybe you can try that paper. That is relevant to the style GAN mechanism. That was a paper I referred actually.
yeah. Yeah, sure,
Yeah,
sir.
ma'am.
Thank you so much, sir. Thank you.
Yes, ma'am. Yes, ma'am. Thank you, ma'am. Thank you so much. Okay. Any other queries from anyone?
I don't
Queries or
think, Jay, we can continue.
yeah, ma'am. Okay. Maybe I can find the paper. from 3D portraits to 3D realistic. This is a paper name, I think so. I forgot a long back. From Arsif. Joe. I don't get it exactly, ma'am. Maybe I can refer that paper some later point, ma'am. That particular paper. That will be interesting paper and would be helpful for you. Yes.
Yes, sir. Sure, sir. Thank you.
Yeah, ma'am. Yeah, ma'am. Okay. So yeah, so this is a source code which I'm going to refer now. So this source code is available in my repository. So this is my repository. I'll ping the repository in our group. So this is my repository. In my repository, the source code we're gonna discuss is all about the GAN. Where it is? GAN. Somewhere it would be repository grown. Okay, yeah, here it is. In this place, you can find source code mnist. So this is a code we're gonna discuss right now. Yeah, this is a source code we're gonna discuss now. Okay, so now I'll share this with you all right moment itself. I would forget later then. Okay, here it is. This is my repository, and within this repository, this is a source code we're gonna design. And in this source code, what we're gonna do in the sense like we're going to generate samples. Anyway, I have ran this code before the presentation itself because it would take a lot time. It's a 50 epoch, so I ran everything now. So now what I'm going to do, I have shown in the presentation, right? What we discussed some time ago. All right, which one? Go back, go back, go back, go back, go back. Must be somewhere. Yeah, here it is. So I'm going to give a noise to my noise to my generator, and real samples to my discriminator. I'm going to make my model to train to generate a realistic images as like this, the fake samples as like this. This is what I'm going to do it now. So now in the source code, I'll explain the step-by-step source code, of course. And before that, I will show you the output first so that you can have a wisdom of thoughts, what we are going to do, of course, right here. So this architecture is like a generator and discriminate architecture. So like encoder and decoder architecture. And here I ran this architecture for almost 50 epochs. I ran it before like 40 minutes before itself. I ran this model, and I have given a noise image. This is a first epoch, very first epoch. You can see that there is a noise images. This is a samples I have given into, I mean, this is a noise data I have given to my generator. During first iteration, my GAN doesn't understand anything at all because it doesn't have any samples given to it, right? So first iteration, after first iteration, discriminator gives some ideology to the generator. Now the first epoch, very first, second epoch, you can able to see. Now it's trying to understand something else. Now you can ask me a question. Okay, sir, very first epoch itself, models tries to understand something. Why did you run it for the 50 epoch, sir? Why doesn't make sense, right? You may think about it. This is a grayscale image. This is a very grayscale image. Maximum the image regions between a 0 to 255. So of course your model doesn't take much effort to understand. But of course we'll not deal with the grayscale images. We always treat the architectures with the color images, so like a 3D images, RGB. So at the time it will be taking a huge amount of time. Here the feature is so very less. That's what I have used like a minced data as a base data. And of course for this kind of data sets only we can able to run in a Colab without pro versions. Okay, now you can able to see the second epoch. This not second epoch, sorry, this is after some amount of epochs, this and all. Okay, this is a fifth epoch. I'll show you the fifth epoch results. Now you can able to see first epoch, some improvements. Still there is a lot of noises was play around across there. And after 50 epoch, it tries to make something understanding. Still we observe a lot of noises which is play around right there. And now we can take a look at the 10th epoch, how it actually transformed. It's quite better, but still 8 is not proper, 7 is not proper. This number we don't able to identify what exactly it's try to say. This one you do. And don't think that most of the people when I show this demo, they thinks that okay, this is copying the actual samples from it is copying the actual samples and pasting it here. Please don't think that it is a generated samples. This 100 images, right? This is like a 1 2 3 4 5 7. So okay, sorry, 10 cross 10. So 100 images I generated right here. So this all these 100 images is a new images apart from the 60,000 minced data what we have given to the model to train data. Okay, this 100 samples is like a, now we have a 60,000 100 samples. Okay, that's all. Now you can able to change the code to 100 samples to generate. So 61,000, 5,000 data, you can able to do it. Any numbers you can able to generate it. And now I can go for 20th epoch. Here it is a 20th epoch. So now you can able to see the little improvements with respect to the number edges and the corners. Now we can say that most of the numbers is trying to identify it. And 30th epoch, I can take you to the 30th epoch. Here it is. Yeah, much more better, much better, not more better, actually much better. Now it can able to see. And the 40th epoch, it makes a little more sense to you. Yeah, quite better. And even 50th epoch, 46 47 is there. I don't find 50th somewhere around. It must be 54. Yeah, maybe I'm losing somewhere else. So maybe 46th one, the recent one I able to see. 46th epoch. So it makes sense. So you find that, right? You can able to see still there is a noise is notable. So here noise, here noise, here noise, here noise. Think about it. This is a very base samples. This is a very base sample. So without what is that? Very base samples without any colors or something else. But still it is having a noises across each and every images. Still there is an unclarity in some images, but of course it has a drastic differences when compared to other when compared to the first epoch samples or something else, right? So 10th epoch, when you compare to the 10th epoch with the 50th epoch, of course there is a lot of improvements are there, but still noise are there. So if you run this same source code for 100th epoch, I would say we may have a good results. Okay, so this is a GAN architecture output is. Now I can get into the, now I'm taking it to the source code so that you have a better ideology now. Okay, now here it is. One second. Okay. So now you can able to see these are all the necessary imports which we have to do. This is a torch here. I'm using like a torch visions because this is a simple project which I'm going to do. So I'm not using TensorFlow right at this place, as it is a very what is that? It's not a very base project, but of course like a small scale project. So that I'm using a torch as a base here architecture, and from torch I'm using like a neural network architecture and respective functionalities. I'm creating an object for everything. Now I'm importing the data loader and the data sets, transforming the data set and saving an images. So necessary imports I have made it here. These are the utility packages I have imported. So NumPy, datetime, Moses and everything. So now this is not required for locally. Now this snippet is nothing but this is a get sample images, and here you can see that the resolution. Okay, I'm generating 100 samples. Okay, I'm generating 100 samples with the resolution of like 28 cross 28. Okay, so with the resolution of 28 cross 28, and the overall results I'm concatenating within one list. That means nothing but the samples we are seeing right here, right? In order to generate this image, I'm using this functionality. Okay, this is a noise data. This is a overall, like I'm generating the noise data, and now I'm giving to the generator the blah blah blah, that and all. I'm not going very deeper. Now you can see the view. I'm creating a view like a 100 cross 100 100, actually 100 samples I need to accommodate here. And each samples you can able to see like each samples you can able to see 28 cross 28. So because minced data resolution is of course like a 28 cross 28, that is the image resolution. And I wanted to fit it in this overall image, right? That image is size is like a 280 cross 280. That means width and height. Okay, width and height is like a 280 cross 280 resolution. And so 10 samples, and of course like a 10 times 10 times is 10 10 10 10. That is what I'm generating in images and concatenating each images on top of this particular Canva. That's what I'm doing it here. That's what my each and every code is going here. Okay, this is a purpose of this message. Of course this will be called at the last of the code. Okay, so now I'm going to the actual architecture. So this is my discriminator architecture. Okay, so now we can consider your discriminator architecture. We are constructing, this is your discriminator, and here you will be your generator. Okay, and your discriminator, you can see that constructor. Okay, constructor, I'm using an input size is like a 784. That means you have a input neurons is like a 784 input neurons. 784 input neurons, and number of class is like a 1. That means the final output layer is like a 1. This is going to say whether this a generated image is a original or not a original. Okay, generate actual image or not an actual image. That's what is going to classify. And you can ask me why is it 74, 784. I'll tell you that. Okay, nothing but actually 28 cross 28 is a 784. That is a resolution. That's what we have a 784 images, 784 pixels. Okay, 784 pixels to form a one simple mainstream data set images. And now I have a sequential architecture right at this place. I'm constructing a sequential architecture. So now the input size is all about 784. The next new hidden layer one is like a 512. So hidden layer one is 512, hidden layer 1, and the next hidden layer 2 is like a 512 256. So 512, another one is a 256. Likewise, I'm constructing my architecture, and another final layer is like a 256, other hidden layer is like a 256 right wise. Okay, and finally number of classes 1. So now I constructed my architecture. You can ask me a question. So okay sir, what is the activation function we are using? So an activation function here I represent like a leaky relu. Leaky relu is nothing but it's like a relu is like a, this is how the relu looks like, but this is a leaky relu, so that we are leaking 20% of the data. That means I'm telling to my model, you can consider some of the negative values also. So instead of, because in the relu is nothing but rectified linear unit, it just considers only the positive values. It never considers any negative values. All the negative values will be converted into zero. So that is what relu will do. But leaky relu, this is a generative architecture. This is a generative architecture, right? So generative, if you wanted to generate a new content, of course you should know the all the information about the previous person, then only you can able to generate new content. So that means positive or negative information you must know. Okay, that is how the generator architectures will be having a activation function as a relu as an activation function right at this places. Okay, and finally is like a sigmoid. Sigmoid is the output layer. Your output layer is defining like a sigmoid as an activation function. Okay, because the output is depends on 0 or 1. Okay, now it's clear. So now this is a establishment function, it's a forward function. As a similar on the same hand, you can see that the generator, I'm creating a generator function class, and I have a neural network inheriting the neural network module right there, and my input size is like 100. That means my input size is like 100. What is that input size? I told you here is like a noise images, so noise samples or noise values. So that is a z. So noise values I'm giving here. My final output is about like my generator will generate images with the pixel size of 784. That means my MNIST images, with my MNIST images 784 pixels. That's what I have represented right here. Okay, so and in between the same process, so a sequential layer, with the sequential layer like a 128 neurons, blah 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 blah, blah 128 neurons, and a leaky relu again. So there is a leaky relu again, and other layers and everything same, like other layers, everything blah 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 blah. So okay, this is a complex architecture as it is how we generally know. So now it makes sense to you, I think so. So what is a generator? This is my generator body, and this is my discriminator architect framework. We constructed everything, and finally you could have noticed that I'm using like a tanh function. So what is the meaning of tanh function? So generally you know it, right? In RNN architecture itself, we'll be using a activation function as a tanh. That means to predict the next word, we should have a knowledge of the previous word. So to predict the next word, okay, you should have all the knowledges of the previous word. That means till the negative values to the positive values. That's what we are using a tanh function right here. Okay, I'm hearing a noise somewhere around. Somebody's unmute, I think so. Could you please mute yourself? Um, Somebody is unmute, I
Let
guess.
me do
Could you
it,
please?
Jay, please. One
Ah,
second.
yes, thank
One
you, ma'am.
second, Jay, I'm doing.
Ah, sure, ma'am. Thank you, ma'am. Yes. Okay, so this is my Janet. Thank you, ma'am. Thank you so much, ma'am. Yeah, so this is my generator architecture is all about. I have constructed my generator architectures and everything. So now noise data, it's a samples, it's like 100 samples is a noise samples. That means some people do ask me, okay sir, what is a noise or what it exactly represents? It's a random values. It's a very random values. It's like for example, I'm taking one array. Okay, I'm taking one array with 0.001, 0.00. Likewise, some noise data. So likewise, I'm randomly giving a noise data to my model, so that because with this noise data is not going to do anything, that I know it, right? So because your generator will not have any data at all. Okay, so now what I'm doing in the sense, I'm creating an object for the discriminator. I'm creating an object for the discriminator. I'm running that model into the CUDA engine. Okay, CUDA engine. Okay, so discriminator, and I'm creating a generator architecture. So this is my generator architecture, and the noise data I'm giving as an input. That means the noise data I'm giving as a input to my generator. So up to this we are clear. Now I'm creating an object for transforms. What is the meaning of transforms? In the sense, transforms compose transforms to sensors. Whatever data you are using, convert the data to tensors format. So tensors format is nothing but like a, you can see the numbers. This is how it looks like. Oh, sorry. It's also like an array, but it is like a very compact and the complex array. It looks like. Okay, this is how the your tensors arrays as looks like, with the depth of like this. You can able to looks like in specific way. I have a numbers, not this one, this one. This is a way maybe it looks like. Okay, your sparse and the what is that, the tensor data would looks like. Okay, so now here, and next one is I'm normalizing my data like a mean and standard deviation. Whatever data it could be, I wanted to normalize my data set within a standard of like a 0.5 and a 0.5 mean and standard deviation. Okay, now I'm creating an object. So that is nothing but actually, now I'm going to purchase a product. Okay, so before I'm purchasing a product, I'm customizing that product. I'm expecting the product in a tensor format. I'm expecting a product to be received from the receiver end in terms of like a mean and standard deviation with a 50%, 50% standard deviation, 50% as a mean value. So this is what I'm expecting. That's what I'm telling to my model. That's what I'm telling to my data set before I download. Okay, and I mentioned one thing I forgot actually here. You could see in batch normalization. So I hope you know what is a batch normalization. So since the architecture is becoming so complex, we have to add this normalization layer, batch normalization layer, to make sure your architecture is so stable and all the values are well aligned with each and every layers. Okay, so that's what the match normalization represents here. So now I'm downloading the dataset, MNIST dataset MNIST from the root function of the PyTorch framework, and trained data. Of course, I require a trained data. When you download this dataset, when you download this data, please transform in such a way. Okay, so to tensor format, don't download in an image format, download in a tensor format, and normalize each and every data in terms of a mean and standard deviation as a zero point 0.5, zero point 0.5. Okay, now you can see the download. I'm downloading the data set. Now I'm keeping like a batch size. So when I'm downloading it, I'm downloading in terms of the batch size. So now I'm loading the data set. I'm loading the data set like in the memories data set, batch size in the 64, shuffle true, drop loss true. Okay, so now I have downloaded the data set. Now data set part is done. So architecture constructions are done, and my downloading the data set part is done. Now the next step is about like a loss function. So I need to define what is a loss function. I'm going to use it here. And so criterion by a binary cross and trophy loss, because since it is a binary cross and trophy problem, so I'm using like a binary cross and trophy. And a D optimizer discriminator, I'm keeping on optimizer. For generator, I'm keeping on optimizer. And for Adam optimizer, so Adam, both of them using a Adam optimizers. And the learning rate, it's 0.0002. Of course, it's a very less, but it would be much more helpful to have a bit accuracy to the models. And beta's version like a zero point 0.5 and a 0.999. And this is for to make sure my model going in a good direction. So if my model during the phase one downs, in the sense, I'm adding as a, I'm considering these are all the beta values to pull that out. Okay, so now I have defined the I defined the optimizers now. So now you can able to see my loss functions BCE will be right here. My loss function, I kept it here, and Adam optimizer I have defined. My Adam optimizer will be defined right here. Okay, so now all together I see that epochs, defining the epochs, and the step I'm making it as a zero to steps as a zero steps. Gen critic, so critic step is starts from a one. Okay, this one I'll explain you when I'm talking about the loops. So now I'm creating a other sample. Actually, this is for D labels and this is for fake labels. For discriminator labels once, that means I'm creating a simple canva. Actually, I'm creating simple canva is like a with the one labels, with the one data. That means it's a white data. Okay, the fake data is completely like a black canvas. The 280 cross 280, I'm creating, so 28 cross 2080 28, I'm creating a some canva images with the black and white in order to compare with the real data. data. That's what I have created this one. That's, and that also I'll tell you how we are comparing it. Okay, now we can get into the step. Okay, so 50 epochs, right? So first epoch is happening. First epoch is happening. So within first epoch, if I have a 50,000 images, all the 50,000 images which comes into the game, right? So now I'm downloading. Now I'm taking the data loader, each and every images. I'm taking it now. Okay, so now I have images. I'm reading images. So I'm giving that images. That means I'm giving that images to the discriminator. So that means we are enabling the discriminator first. We are having a real samples. We are having a real ground truth data here. We are giving it to the x to the d of x. We are executing it. So once it executes, it will be generating some images. That means we have a criterion. So x output in the sense the output is generating by this, and d labels. So d labels in the sense this is a positive labels. Now it is comparing with this one to this one. Okay, now this is comparing, this will generating for with respect to the real samples. With respect to the real samples, by default it will be samples, it will be generating some data. That sample will be compared with the d labels, because in order to calculate the loss function, right, initially iteration we will not have any data at all to compare. That's what we are having this ground truth data in by default. Sorry, by default to compare that. By default to compare that. Now we are calculating dx loss. That means discriminator of loss. That means the equation I have taught you, right? We are calculating dx loss. This loss, discriminator loss for the real data set. So that's how we are doing right here. So the next one, what I'm doing, I'm having a sample noise data. So I have a noise data right here. So this noise data I'm giving it to the generator. Now you can able to say I'm giving it to the generator. Now generator takes the noise data. Generator takes the noise data. It's generating the fake samples. That fake samples we are giving into g of z. We are giving into to whom? The discriminator. Okay, now discriminator generates some outputs, right? That is the actual outputs. That is the actual outputs, right? That output should be compared by some input. Am I right? That output should be compared by some data. That data is like a defix. That is the initial data. Okay, because initial iteration we don't have any samples to compare at all. That is what we can mention it as a defix right here. Okay, so now after this we have a dz loss. That means your discriminated loss towards the generated fake samples. Okay, so now this is a loss I'm calculating. So dz loss is computed. So dx loss is computed and dz loss is computed. Now summation of concatenating them, we are getting the overall discriminator loss. That means overall discriminator loss for your architectures for the d loss. This is the two things. Okay, now you can see, now I'm updating the gradients of the zero. I'm setting the zero gradients for my discriminator, and I'm updating the backward propagation. So backward, I'm initiating the backward propagation, and I'm optimize a step-by-step optimization. So okay, that is in the odd atom step optimization 0.0002, right? So I'm setting the zero gradients initially and the back propagation and optimizer step. Everything will be happening right here. So now this first iteration just came here. Now we can able to see n step is 0. Okay, n critic is the 1. Okay, so now which is equal to 0. Of course it will be equal to 0, right? So now we are going here. Now what happens in the sense, again we are doing taking the noise data again, we are executing the d of g of z again, and we are getting the z output. So with this output we are calculating g loss. So gray, I mean generator loss. Generator loss, we are calculating the same equation. Generator loss, we are calculating the generator loss right here. So now we can see completed generator loss. We have to kickstart like a back propagation of a generator right in this place. That's what I'm setting the zero gradients right here, and I'm doing the back propagation again and the optimizing things here. So now this iteration is happening so over the time, but nothing but actually initially we are giving these real samples and we are computing some laws and everything, and finally this computes some value and give it to the generator will generate an images, it will compare, generate, then it will go. This process will happen over the time period. That's what I have written in a for loop. The same process I have written in a for loop. Okay, so now if you see this, I'm telling to my model like a each step. So each steps like each steps like a 500th step. If you are reaching like a 500th step, please hold the process, please hold the process and report me what is the actual loss and what is the G loss and what is the actual D loss. I'm just reporting right at this place, and you can able to see every thousandth iteration you can able to see D loss and G loss again. That means I'm reporting right here. Okay, so that means I'm stopping the process with every 500 and 1000 samples. You can see 500 1000 and 1500 2000. Every 500 steps, every 500 steps I'm stopping the process, and I'm just getting the laws and everything. Now also you can able to see, so for first step you can able to see 1000 so only two sample two up to 100,000 steps it's running across. Okay, and the second you can able to see under 2 G losses. So I'm just limiting it maximum 1000 steps, not greater than 1000 steps, because your model will run for the more runs also, but it will take more of us time and we cannot able to run it in a collab, of course. And also you can able to say losses seems like a very higher. So yes, of course it will be higher, I agree to it, because if you're running it over the time period you may experience some losses is reduced, but you can't able to reach the executing exclusive results until unless you're running for the more epochs, until unless you're allowing your model to go for the more steps to run across. So now we can able to almost I ran it for like a 46,500 steps. I allowed my model to run, and my collab supports for this. And if I able to run the same code for another 20 minutes, it would run. But more than that, it will not run, of course. Okay, and this is all about this iteration, how this model is actually works. Now also you can able to see this is a final output which I'm generating. Okay, this is a final output of I mean the 50th epoch images. That one we have already discussed. And finally I'm storing these models in the name of like a discriminator as a pickle object, and a generator as a pickle object. I have stored them right there. Okay, so same thing actually. Now I have a same thing which I have done so far in the steps. And you can see one more thing also. I thought of showing some videos to you, and I am tutorial presentation, not this one. Here I have one source code actually. Sorry, so one video I would like to show. The GAN architecture, GAN, diffic AI. Yeah, this is one paper which helps you to understand. Audio is not important. You can just have a look at the video alone. Um, so the overall flow, what we did. So in this paper, this is one of our, actually it was a very old paper. Now we have a lot of trendy and fancy papers was released, and this is a place where they have talk about like a shorts related GAN architecture generated. So now you can see, observe these pictures. You can able to see we are taking the facial landmarks of a particular person from the one driving sequence. We are applying on top of different training frames, and that of course that landmarks should apply on top of every images. That training samples also should be related to it, or else you will face a lot of glitches and errors. Here you can able to experience that you can able to see the lot of glitches and everything. And this is a shorts of learnings, like they are saying like with the help of a few shorts learning we can able to get the accurate results with respect to the portraits, not for the overall image or overall video generation or something. For few shots we can able to attain some amount of quality based transitions. And this is for an images actually. So far we have done the same concepts are applied to the things what we have done. And for images, is it possible to generate an images like this? Is it possible to do by ourselves? Is it possible? Yes, of course it is possible. I have some videos source code also, but I don't think so it's not a right time to show that. Okay, so this is a one thing I wanted to show with you all, and now I can tell you another interesting factors. Where is that? Yeah. So in my GitHub repository, if you go to my GitHub repository, Okay, so in this source code, what we have done is completely like images of grayscale images. Like okay, so we are not dealt with a very complex structure or by the way anything else. But if you go to my repository, you could have spot. Where is it? Gan. It's yeah, here you can see I have a three different data sets. One is like a MNIST data set, it's completely grayscale. Another one is like a image data set. Okay, image data set is like a CFA data set which you might aware of like a, and another one is like a car. This is like your manual data set. So I have tried this model with a car, my own car images. I have created some different Lamborghini kind of images, some Honda images, Honda cars actually I've generated. You can use this source code for like a MNIST itself. You can able to see there is a multiple source codes I have right there. Okay, I have a source code of like what is that conditional vanilla can we have seen it now. So same source code, actually same thing I have used in a conditional kind, same source code, there is no much differences in there, but I was added some conditions on top of it. Okay, so I have added some conditions on top of it. This is how I'm expecting my model to generate. So I'm adding some set of conditions right at the place of generator here exactly you can see. Mm, Here I'm adding some conditions to generate some images with respect to this. There is a while sampling this condition size. Yes, you can see this. So I added this condition size. So with respect to this condition size, you can able to fine tune your images to be generated in different dimensionality. So this condition size I have given into everywhere. I'm giving with respect to the condition of image size actually I have given. So now if you wanted to have like you wanted to generate only the 8 samples, I mean the from MNIST data set we have a multiple images, right? 1 2 3 4 5 6 or various samples are there, right? If you wanted to generate only like a five number and 6 number or 8 number, in the sense you can able to utilize the same source code and you can able to do it. And also on another hand, like I have other one is like infogan. So infogan also it makes sense to use, so which helps you to understand how these images are generating and everything. So please try experience it out. And also please try this CFA 10. This is the images of the color images. Okay, so this color images is very much helpful for you. Most of us will work with the color images, there is no doubt in it, but in the color images it's not a big deal and all, simple actually. So we'll be giving like a 28 cross 28 here, but instead we'll be giving like a 32 cross 32. That means 32 in the sense, see for image size is like a 32 cross 32 each pixel size, and the what is that RGB is like a 3. So that's what we have given as a channels as a 3. Okay, that's how I have dealt with. And also when you are generating the final samples, your canvas should accommodate the color samples too. That's what I mentioned as a 3 right there. And not much differences. So when you're constructing a discriminator architecture, you have to do some fine tuning in the linear layer and fine tuning in the generator architecture construction. So that's all. The generator, you have to generate images like a 32 cross 32 with the 3 channels. That's all, nothing much differences. Yeah, normalization of course will not be having a grayscale images, RGB. So I'm mean and standard deviation with respect to 0.5 across. That's all with respect to the color images. It's not a big deal at all. Almost if you compare that, all the source code is completely same. Nothing much worry about these things. So color samples is also almost the same. Okay, so this is about advancing CAN inversion actually. Yes, sir. So this is all about, yes, this is a paper about, yeah. Yes, any doubts with respect to this source code, what we discussed now, and I have shown you some of the source codes which is relevant to what is that, like color images, how to deal with the color images and everything I taught you now. Any doubts or any queries do you have in your mind? Almost we are close to the end of a session.
Participants, any doubts?
Any doubts or any queries? And ma'am, Preeti ma'am, I think so, who asked this. This is a paper, ma'am. This is a paper I spoke about, ma'am. So 2D portraits to 3D realistics. This is a GAN inversion technique, and you can see in this paper there was a style GAN technique and some tool they have used like EG3D. This is a tool actually I mentioned. EG3D utilizes a triplan representation, right? This is what actually I told, ma'am. This is a paper is all about. Maybe this is helpful for you, I guess.
Yes, sir. Got it. Thank you.
Yeah, ma'am. Any doubts or any queries on top of this GAN architecture?
I don't think they have any queries as of now.
Okay, ma'am. Okay, ma'am. So I hope you are good then.
Sir, if you don't mind, I do have one more doubt.
Yeah, please, ma'am. Go ahead, ma'am.
Yeah, if you're generating like this, how do we evaluate it?
Yes, that is
What is the authenticity?
so for example, ma'am, if you are doing like matrices, if you're expecting through the matrices for VLMs, now you are doing the same concepts, you want to use like a same GAN inversion technique that is available in a VLMs also. If you are generating through the VLMs, so we have a various metrics like a blue matrix, the rouge matrix, and all everything will be there. So that matrices you have to use to evaluate the model comparisons. But if you don't have that, and of course, if you're coming to the GAN architecture, we have a what is that? So how we will be evaluating through CNN architecture? So we'll be having like a true positive, true negatives, and all, right? Similar thing we have to evaluate, ma'am. So similar classification reports we have to use in order to compare the images with the ground truth to evaluate this matrix as a precision, recall, effort. So the traditional matrices, ma'am. There is no options at all for see this kind of architectures.
Whether human feedback could be considered as one of the evaluation metric?
Human feedback. This is not like some mechanisms that we are doing it, right? Maybe from human feedback in the sense like if you fine tune any architecture now, for example, if you changing the data sets or something else, then we can able to do because if you go for like a VLMs, then you can able to add like a human feedbacks. So through the feedbacks, your model evaluation, your model enhancement will be little higher. Then you can able to evaluate through some blue and rouge matrices or bird matrices, which helps you for you. But this GAN architectures, there is no human intervention will takes place at all, right? Until unless we changes our data sets, until unless we are fine tuning that architecture, fine tuning the hyperparameters, we never make anything changes at all. So there is no human interventions will be there at all, right? Here.
Yes, sir. Thank you so much.
Yes, ma'am. All right, ma'am.
Good evening, sir.
Yes, ma'am. Please, ma'am.
Yes, actually, we need some pre-processing of these data sets, right? When we are implementing as this as code, we
Mm-hmm.
need some pre-processing, right?
Pre-processing in such a way, ma'am. We wanted to crop that images kind of things and all, right? So which area you wanted to focus on? That's what you meant to say in pre-processing in the sense.
Yes, sir.
Yeah,
Yes, sir.
ma'am. Yeah,
That was
yeah. Of course, you're right, ma'am. Yeah, yeah. So I got your question. So when you're giving into the discriminator, of course, you have to do some pre-processing before you're giving into the discriminator. Instead of like
actually
your
this.
folk.
Yes, sir. Yes, sir. Yes, pre-processing is actually related with the accuracy of that model, no, sir.
Yes, of course, ma'am. That's what. So that's what in our GAN architecture where we are giving the data set. So our data set issuing area is only the discriminator, and before giving it to the discriminator, we have to fine tune our. So we have to pre-process our images the way you want it to be. So for example, I have a minced data in a various. So I'm just pre-processing it in which area I wanted to crop and which of the data I need to give it to the model. Of course, the pre-processing is mandatory before you are approaching the discriminator architecture. Discriminator architecture, you should give the very straightforward data rather than some noise data, rather than some invalid samples which is present over there, ma'am. That is very important. So for that case,
Yeah,
of
thank you,
course,
sir.
we'll go for
Actually,
yes. That for that case, we can go for like a,
yes,
some computer vision techniques to handle that images, so thresholding and smoothing kind of things and
actually
all,
I'm
ma'am.
doing GitHub profile set now.
Okay,
So
okay,
it's
ma'am.
having many introduction part to high level coding implementations related to this artificial intelligence. It's very good, sir.
Thank you,
It's
ma'am.
very
Thank you,
useful
ma'am.
for us. If we are starting to learn this machine learning concepts, it's very useful for us to implement these concepts, which you have given very clearly in GitHub profile. Thank you.
Yes, thank you, ma'am. Thank you, ma'am. It means a lot to me, ma'am. Thank you, ma'am.
Yes.
Uh, so
Hello.
Pooja ma'am is on the queue. Pooja ma'am. Pooja ma'am, if you have any query, please ask. Okay, Shivani ma'am,
Yes, good evening, sir.
please.
Good evening,
Good
ma'am.
evening, ma'am. Good evening, ma'am.
Sir, I have two questions. First
Mhm.
of all, So can you please just tell me what is the main difference between this discriminator and encoders?
Uh,
And all,
mm,
yes, sir.
please, ma'am. Next one, ma'am.
And the next question is like there are different models of GAN are available like SG GAN, CG GAN, vanilla GAN. So suppose I am working in the agriculture field. So can you just suggest me like which GAN model we will use to regenerate our images? Because in medical field, so there is a need to generate more data, as
Mhm,
well as in agriculture field also we need to generate more image data. So
mhm.
which models are most popular, or you please suggest like from where we can start with?
Yes, of course, ma'am. So now, for your first question, to answer your first question, so encoder, difference between an encoder and a discriminator. So discriminator is all about comparing the two samples and will be generating the final images. It's not dealing with any specific features kind of things and all. But in your encoder architecture is more or like it takes a picture and extracting the features and which is playing within a latent space. This is what your encoder will do, but discriminator is comparing the features with the one other some other images to have a better resolutions. This is what your discriminator does. This is the answer for your first question. And the
Okay.
second thing is that is which GAN is best in the sense that is based on your problem statement, ma'am. If you want to for agriculture, you are focusing on only the crop area, or if you are focusing on only some set of plants, what is some set of plants classification, or you are focusing on some plants diseases in the sense if your area of pictures or if the features of your pictures if is a very less in the sense, I would suggest like a normal convolution GAN architecture, ma'am. So convolution GAN architecture since you can construct a generator and a discriminator as a very base architecture as a GAN, and you can CNN and you can go for. But oh, no, sir. Actually, in my agriculture, I'll be having a various features, sir. I'll not be focusing on only simple plants, sir. I'll be having a various plants. I'll be covering the large area. So that time,
Mhm.
what kind of architectures I should go for as a generator and discriminator? Of course, you have to go for deep convolution, ma'am. So that we have a lot of features to focus upon to make your discriminator to understand your generator to generate. So that you have to go for some complex architecture. So in sample, I can tell you that. So now, however, we dealt with the CNN architect. I mean the images only, right? But you can see that I have used a simple neural network architecture here. So we since we are using like a MNIST images of 28 cross 28, I'm using only the neural network architecture here instead of using a CNN. Reason is nothing but because my image sizes are very less. So 28 cross 28 maximum 784 pixels. That 784 pixels I can able to accommodate in a single array itself. So 784 pixels maximum my neural network architecture itself can able to understand. That's what I'm extracting images as a numbers. That numbers I'm giving it to the neural network, and finally I'm reconstructing that images. For example, if your image size is a quite larger, that means like 1000 cross 1000 or 500 cross 500, that time you have to go for CNN architecture because your image is bigger and your features of your image is also of course is bigger. Then you have to migrate to some complex architecture. And also, ma'am, it's not mandatory. You have to construct your own CNN architecture. We can directly take some VGG 16 as a what is that a pre-trained model, pre-trained VGG 16 19 pre-trained model as a generator, and what is that VGG 19 or 16 as a discriminator. So some additional layers we have to add to adopt on top of a GAN architecture, ma'am. That's how it works for you.
Okay, okay, sir. So, also one more question.
Please, ma'am.
Suppose I'm using discriminator and the generator and the discriminator. So, is
Mhm.
it necessary to use the same number of the layers, convolution layers in the generator as well as in the discriminator?
No, ma'am. Of course not. Because, ma'am, generator, discriminator, both of them should be powerful. Having said that, I don't say like a, for example, generator, I have used these many layers, and the same number of layers I should be implementing on the discriminator. Doesn't mean that, ma'am. So for generator is a one is going to do a higher role. So I'm using almost like 8 layers or 9 layers here, but the discriminator is going to just compare the values one with the other one. So that I'm keeping a less layers here. So that means here only I'm using a 3 layers. But if you're focusing on, okay, sir, instead of going for 3 layer, I can go for 2 layers or 1 layers, and then your model will fail, ma'am. So it must be powerful based on the capability of the models generation you're going on. It's not mandatory. You have to focus on 100 layer here, 100 layer here, ma'am. It's not mandatory.
Okay, okay, sir.
Yes,
Okay,
ma'am.
okay. So suppose in my data set, so I am taking suppose the images.
Mm-hmm.
One side I'm taking the images that contain only one disease, only
Mm-hmm.
one leaf image is present in which disease is there, and on the
Mm-hmm.
other hand I am having one image which is having different plants, and different plants is having different diseases also. So for that, I need to use complex GAN models like vanilla GAN or
Mm-hmm.
these SG GANs.
Of course, you have to go for some complex GAN, ma'am. But the thing in the sense, like if you confuse your architecture will confuse. We have to give the very straightforward data because, however, it's a neural network architecture. So if you're focusing on one area in the sense I'm giving a multiple diseases, I'm creating a new diseases. If you do in the sense your GAN architecture will surprise you with new disease images, and
Okay,
you
okay.
will be surprised with data set. Again, you have to create other architecture to classify what disease it is.
Yes,
So that
yes.
you can take one sample. For example, disease A in the sense you can take 1,000 samples of disease A and you give it to the architecture. Let's create other 10 samples of that disease A. So that's what. If you give your 5 samples mix panni given in the sense that's it. Your
Okay.
architecture will give you like a corona mari or different it will come.
Okay,
That's
sir.
what.
Okay, sir.
Yes, ma'am.
Thank you,
Yeah,
sir.
yeah.
Thank you, sir.
Thank you.
Thank
Yeah, thank you, ma'am.
Jay,
Bye,
one
bye.
more person.
Yes, ma'am. No, it,
Mani
ma'am.
Megalai, ma'am. Ma'am, Mani
Ah,
Megalai, ma'am, please.
Good evening, sir.
good evening, ma'am.
Sir, I just have one question with respect to
Mhm.
whether can I use GAN in content-based image retrieval, sir?
Content build retrieval, ma'am. So how your data set
Content-based image retrieval.
content based in the sense of what does the meaning of content exactly you mean it, ma'am?
Sir, any content what I wanted to pull from the image data set.
Mm, that is based on your images, how it looks like, ma'am.
Yes,
Is
Like
it
yes,
that?
yes, yes.
she wanted to say that a boy with a ball, like such content.
Correct,
Oh, okay,
correct.
okay, okay.
Um,
That means like what we say like
I give an image. For example, I give an image of a tree.
mhm.
I should be able to pull out all the images with respect to the same tree, whatever I'm trying to project there. So
Okay,
can I
okay,
use
okay.
GAN for that?
Yeah, ma'am. That is actually related to like what is that? The soft and hard attention mechanism concepts. Actually, yeah, you can go ahead to use it, ma'am.
So I have to
Yeah,
use
it's
both there, the generator as well as the discriminator, sir.
yes, of course. If you are focusing on generating a new samples, we have to use both. That's what, ma'am. We can able to use only GAN architectures too. I mean generator architectures too, but we will not be sure how equipped that the generated content is about. So in such place, we have to use a discriminator.
Mm-hmm.
Okay, you can
So
able to
will I
generate
have
an
to
images.
face,
Mm-hmm.
okay, will I be able to have any challenges into this, sir?
Of course, there will be a lot of challenges, ma'am. When you are focusing on the content based, right, it will be having a some amount of features when compared to the straightforward images. Content images will be having a 2 to 3 features additional extra. At the time, your
Correct.
architecture will be focusing on various attention. So soft and hard attention it will be focusing on. So which images, which feature I have to focus on in primer, and which feature I have to focus on the secondary level. Likewise, it will be giving other kind of things and all. So it will be quite challengeable. Of course, there is no doubt in it. You have to work on high number of epochs and proper
Mm-hmm.
what is that optimization
Data
techniques.
set.
Everything you have to.
Okay.
Data sets are very mandatory. Data sets are very very important for your case, ma'am.
Okay, sir.
Since it is
Fine,
also
sir.
very
Thank you so
nutritional.
much, sir.
Yeah, all right, ma'am. All
Thank you,
right,
sir.
ma'am. Yeah, pleasure is mine.
Hello, good evening, sir.
Hello, ma'am. Good evening, ma'am.
Sir, you discussed about lot of models.
Yeah, ma'am.
Uh,
Yeah, ma'am.
so among these models, which one is the better, sir? Generally, which one is the better? Which one is the preferable?
So preferable one is basically, ma'am. So DC GAN, ma'am. DC GAN is the most widely used, say for image based everything, ma'am. So DC GAN is most commonly used, and conditional GANs would be used in few areas, ma'am. Sometime before, ma'am asked, right, the content based image generation. So at that scenario, you have to go for like a conditional GAN architecture. So most common is like a DC GAN, ma'am.
Yes, sir. Thank you, sir. Sir, can you give your contact details? Because whenever we have the doubts, we can clarify with you.
Sure, ma'am. Here is my contact details, ma'am. Here's my mail
Thank you.
ID and WhatsApp. Yeah, sure, ma'am. Of course. It's like I'm speaking in a FM radio. So any other caller, any other people are joining on the line, likewise I'm talking.
No, no, Jay. As of now, nobody else.
Okay, ma'am. Okay, very good, very good.
Is there any other participants would like to have any questions?
RJJ is waiting.
Till which
Okay.
No, it's just for joking, ma'am. If you have any questions, you can just bomb, but no worries. I'm here to
No,
answer.
I don't find anybody raise their hand.
Okay, ma'am.
Okay. Yeah, I
Okay,
hope
ma'am.
none of them have any queries. Yes,
Okay,
there
ma'am.
is one thing.
Yes,
Kirti Priya ma'am.
yes, ma'am.
Good
Sha.
evening, sir.
Yeah, good evening, ma'am.
Yeah.
Please, ma'am.
Am I audible?
Yeah, ma'am. You are of course audible.
So, sir, recently we've been trying to work on
Mm-hmm,
Down syndrome. We want
mm-hmm.
to apply explainable AI to Down syndrome for the detection.
Okay, okay,
So,
ma'am.
we wanted to use GAN for synthetic image generation of feet
Mm-hmm,
images, like specifically for
mm-hmm.
ultrasound images. So, how feasible is it? And what would be the accuracy based on the approach we want to go?
For your case, ma'am, there is one best option is like a GAN architecture. There is no doubt in it because for your case, you can't go for VLM because since it is a Down syndrome, you have to be very peculiar on images you are focusing on since it is a more peculiar problem statement, right? So you can't go for the VLM. If you blend on VLM, it will be taking you, you have to pay some amount of additional amounts to generate a lot of images. So GAN architecture is one of a base architecture. Is a very helpful to generate such a related images. But thing in the sense it's quite complex, ma'am. For your this thing is like a quite complex. If I see your data set, maybe I can have a good idea, ma'am. A Down syndrome. Is it like
So, like
specific?
the data sets
Mm-hmm,
are specifically the
mm-hmm,
fetus,
mm-hmm.
ultrasound fetus data sets. I hope you've seen the
Yeah, yeah.
ultrasound
I heard. Yes, yes,
images.
ma'am. Mm-hmm,
So,
mm-hmm,
those are basically like we have a lot of edge detection to go for before we even start working on it. So,
mm-hmm.
like, do you advise GAN for use like synthetically generating such kind of data
Yeah,
sets?
ma'am. For image synthesis, of course, you can go for a GAN. There is no doubt at all. That's what you have to construct this GAN architecture in which very peculiar way actually. So our generator part will be very prime role. It will do it here. Discriminator part will be discriminator is not that important, but a generator part is must be very complex since you are
Okay.
focusing on the edges and the corners and all. If you're focusing on in the sense all the edge cases, if you're focusing on, that's very important. Constructing a GAN architecture is a very, I mean, the generated part is very important, ma'am. I would advise, ma'am, there is we have no options, ma'am. First of all, if this option is not in the sense, you have to go for like other image generations like a variational autoencoders kind of things and all. But there you would be facing a lot of noises and the losses, reconstruction loss will be very higher. So for such scenario, you have to blend on only this GAN architectures, ma'am.
All right, sir. Thank you.
Yes, all right, ma'am.
Yes, Jay sir, that previously there was one more hand raised.
Yeah,
Any
ma'am.
other participant would like to have any queries to be clarified? Any queries, please? Okay.
Hello, ma'am. Am I audible?
Yes, sir. There is one person.
Yes,
Yes,
sir.
sir. You are audible. Please ask your question,
Okay.
sir.
Uh, there is no query actually. The thing is that I'm a highly non-technical person. I don't know. Uh, I don't know very much. Hello, am I audible?
Yes, sir, you're audible
Yes,
now.
sir.
Okay, I don't know very much regarding the technical section, but as you all know, there are collaborations, and we need to spend a lot of time with our friends also, with our colleagues also. So there I have seen and learned many things regarding the GAN and all the other things. So thank you for clearing like all the basic doubts or and all the things. The way that you have taught us, that is commendable, and thank you very much, sir.
Thanks a lot, sir.
I just wanted to say.
It means a lot to me, sir. Pleasure is mine.
Thank you, sir. Thank you. Yeah. Is there any other doubts to be needed to be clarified from your participant side?
Yeah, am I audible?
Yes,
Yes, ma'am.
madam. You are audible.
Yeah,
Manjari,
yes,
madam is on the screen.
yes,
Yes.
Manjiri here. So,
Yes.
first of all, thank you, sir. Thank you for the wonderful session.
Thank you,
And
ma'am.
my question is in continuation with the one which is previously asked. Like I have been working on this diabetic retinopathy symptoms. So I need your advice. So how, I mean, it would be good if I take all the images which are generated by this GAN. Uh, I mean, have you ever explored this area also of diabetic retinopathy, retinal images? Ever?
No, ma'am, actually not specific to the medical areas, ma'am, because I do generate an images. I have using the GAN architecture
Yeah.
for scene
Uh-huh.
creation. So I'm working on some autonomous field now. I'm
Uh-huh.
creating various images using what is that? The scene creations, how the objects should be allocated in each and every places while the car is driving, right? In such a way, actually, I have created. But the
Uh-huh.
medical wise, I was not experienced, but it can be. So because
Okay.
I have read some papers too, right? So it can be possible, ma'am.
Okay.
Yeah,
Okay.
yeah.
Yeah. Thank you
Yeah.
so much, sir.
Thank you, ma'am. Thank you, ma'am.
Manjari ma'am, it is possible actually. Why you have such a query, I don't know. What is your actually aim of doing it also? You can better share.
You can reach me out, ma'am, anyway to this number
Yeah.
or mail ID also. I can help you out.
Okay.
Yeah.
Yes, yes, sir. I have taken your number and your email address also.
All right, ma'am.
Mm.
Okay.
Okay. So is there anybody have any doubts? Okay. I hope that many might have been clarified their doubts. And
Yes, ma'am.
Jay sir, I'm very much happy to see that the number of participants who are very much eagerly, actively participating by 9:15 today.
Yes. That's what I about to
And
say.
I was really
Yeah.
wondering, like, you know, how much is our participant strength who have been got approved? It was 593, and
Mm-hmm.
who have actively participating was almost 300 people. So we
Mm-hmm.
are very much happy to have you all here. And let me
Sure,
have
ma'am.
my concluding thanking session for you today.
Sure, ma'am.
And we are very happy to have you here, and we um, show our gratitude towards the concepts you have discussed about how the generator works, how the discriminated works, and what is their role in image generation was very clearly and simply clarified. And also your presentation and your hands-on session, and even the research directions you have given was really helpful. And it is like truly very much grateful for every people who attended this. And also I haven't heard about this Ganzu. Just now I was checking out what is this Ganzu and how it is useful, and what are all the GANs will be used for image processing for the text-based. Everything was clearly mentioned in your lecture, and we are very much happy to have you here as a resource person, Jay sir. Thank you very
Thank you,
much,
ma'am. Thank you, ma'am.
and I hope that our participants also will accept the same. Let us show our appreciation in the form of applause to our resource person.
Thank you, ma'am. Thank you, ma'am. It means a
Thank you
lot to me,
all.
ma'am. Thank you,
Okay.
ma'am. Thank you so much, ma'am. So
Thank
thank
you
you so
all
much for
participants.
yeah, thank you.
Tomorrow, yes, sir. Please,
Yeah,
please
yeah,
conclude.
thank you so much for all the participants who've been here till 9:15. It's really hard, I know. So thank you so much for all the people and have a good rest of the day. Happy Vinayak Chavithi for tomorrow. And thank you, Anita ma'am, and thank you, Agilanda Shiv ma'am, who made this session is really possible. And you people coordinating is very well. And thank you so much, ma'am. Good day, ma'am.
Yeah.
Yeah,
Thank
good
you,
day.
sir.
Bye-bye.
Thank you.
I'm
Yeah,
dropping, ma'am.
thank you, sir. Thank you. Yes, sir. And participants, thank you very much for your active participation and a constant learning. And also the session links was given. That is the response links. That is the feedback link and the attendance link. Both are combined together today, and it was posted in our chat box. That is MS Teams chat box as well as in our WhatsApp chat. And I'm already getting much number of responses so far. I remind you again, till 10 o'clock today, it will be enabled to people. And thank you all for your active participation. And tomorrow, we will be using the same link. Yes, we will be using the same link for joining the session at 6 o'clock. Thank you all. Let me stop the recording.
Anita ma'am,
Yes, madam, please.
ma'am, can will it be possible to get the PPT and the code what sir was using, ma'am?
Madam, as per this norms, we will be
Mm,
collecting all the PPTs, and it will be
okay.
shared through ATAL, ma'am. That is ATAL. And the
Okay.
recordings also you can see through the SharePoint.
Code, ma'am. What sir was using?
Code, Sir code, Google Colab code, if suppose sir is helping us with that, surely once we receive it, we will collect all the PPTs and put it in our WhatsApp group itself, ma'am.
Okay, madam. Thank you so much, ma'am.
Thank you. Okay, people, I hope that you have a very wonderful evening today, and thank you all. Let me stop this recording as well as I will stop this meeting. Thank you.